In the depths of space, there are regions where gravity becomes so extreme that nothing, not even light, can escape. These regions are called black holes. They are not cosmic vacuum cleaners. They are not portals to other dimensions. They are not science fiction. Black holes are natural consequences of gravity operating at its most extreme limits. They are born from stars. They are shaped by spacetime, and they are among the most powerful laboratories for testing the laws of physics. But where do black holes come from? To understand their origin, we must begin with the life and death of stars. The life cycle of massive stars. Stellar evolution describes how stars are born, live, and die. Stars form inside giant molecular clouds composed mostly of hydrogen gas. Under gravity, regions of higher density collapse inward. As material compresses, temperature rises. When the core temperature becomes high enough, about 10 million degrees Kelvin, nuclear fusion begins. Hydrogen nuclei fuse into helium. Fusion releases enormous amounts of energy. That outward pressure balances the inward pull of gravity. This balance is called hydrostatic equilibrium. As long as fusion continues, the star remains stable. But this balance depends entirely on fuel. When fuel runs out. For small stars like our Sun, the end comes relatively gently. But for massive stars, typically those more than 8 times the mass of the Sun, the ending is violent. Massive stars burn fuel much faster. They fuse progressively heavier elements in their cores. Hydrogen to helium, helium to carbon, carbon to oxygen, and eventually to iron. Iron is critical. Fusion beyond iron does not release energy, it consumes energy. Once iron builds up in the core, fusion can no longer support the star. Gravity wins. The core collapses in less than a second. Temperatures soar to billions of degrees. Protons and electrons combine into neutrons. The core compresses dramatically. The outer layers rebound in a catastrophic explosion known as a supernova. A supernova can briefly outshine an entire galaxy. But what remains at the center depends on mass. The critical mass threshold. After the explosion, the remaining core remains. If the remaining mass is less than about 1.4 times the Sun's mass, it becomes a white dwarf. If it is between roughly 1.4 and about 2 to 3 solar masses, it becomes a neutron star. But if the core exceeds the limit that neutron degeneracy pressure can support, roughly about 2 to 3 solar masses, no known force can stop further collapse. Gravity compresses the core beyond neutron density. Collapse continues. According to current theory, space-time curvature becomes extreme. An event horizon forms. A black hole is born. What is an event horizon? Event horizon is the boundary surrounding a black hole. It is not a surface, it is a point of no return. At this boundary, the escape velocity equals the speed of light. Since nothing can travel faster than light, anything crossing this boundary cannot return. It is important to clarify, black holes do not suck objects in from afar. If our Sun were replaced by a black hole of equal mass, Earth would continue orbiting as before. From a distance, gravity depends only on mass, not whether that mass is a star or a black hole. The difference becomes extreme only near the event horizon. Einstein's revolution. Einstein published General Relativity in 1915. In this framework, gravity is not a force in the traditional sense. It is the curvature of spacetime caused by mass and energy. Mass tells spacetime how to curve. Spacetime tells matter how to move. When enough mass is compressed into a sufficiently small region, space-time curvature becomes so steep that all possible paths lead inward. Mathematically, the solution describing a non-rotating black hole was first derived by Carl Schwarzschild in 1916. Later solutions described rotating black holes, which are likely more common in nature. At the very center, equations predict a singularity, a point of infinite density. However, physicists widely believe this indicates a limitation of our current theory. We do not yet have a complete theory of quantum gravity. Supermassive black holes. Supermassive black holes exist at the centers of most galaxies. Our own galaxy, the Milky Way, hosts one called Sagittarius A*. It contains about 4 million times the mass of the Sun. Some galaxies host black holes billions of times more massive than the Sun. How did these form? There are several leading hypotheses: gradual growth from stellar mass black holes, direct collapse of massive gas clouds in the early universe, mergers of smaller black holes over cosmic time. Observations suggest that supermassive black holes formed very early, within the first billion years after the Big Bang. Exactly how they grew so quickly remains an active area of research. Observational evidence. For decades, black holes were theoretical predictions, but today we have strong observational evidence. In 2015, gravitational waves were detected from merging black holes. In 2019, the first image of a black hole's shadow was released by Event Horizon Telescope. The image showed the supermassive black hole in galaxy M87. In 2022, Sagittarius A* was imaged as well. These observations matched predictions from general relativity with remarkable precision. Do black holes last forever? Stephen Hawking proposed in 1974 that black holes are not completely black. Quantum effects near the event horizon should cause them to emit extremely weak radiation, now known as Hawking radiation. Over extraordinarily long timescales, far longer than the current age of the universe, black holes could slowly evaporate. This prediction has not yet been directly observed because the radiation is too weak to detect for astrophysical black holes. What we still do not know. Despite enormous progress, key questions remain. What truly happens at the singularity? Is information permanently lost inside black holes? How does quantum mechanics reconcile with gravity at extreme densities? How did the earliest supermassive black holes grow so rapidly? These are open scientific questions. No credible scientific theory suggests black holes are wormholes, time machines, or gateways. Though speculative solutions exist mathematically, they lack empirical confirmation. Science distinguishes clearly between tested theory and speculation. Conclusion: the logic of extreme gravity. Black holes are not cosmic anomalies. They are the logical outcome of gravity acting without limit. They form when massive stars collapse. They grow through mergers and accretion. They bend space-time to extremes. They emit gravitational waves. They help regulate galaxy formation. Far from being destructive monsters, black holes are essential components of cosmic structure. They are not violations of physics, they are confirmations of it. And by studying them, we probe the deepest foundations of reality. In the darkest regions of the universe, we find not chaos, but the precise consequences of gravity.